Hi everybody and welcome to Organic Chem Analogies. My name is Maria Thomas and today we'll be talking about organometallic reactions and some of the strange things that happen in these kinds of reactions. We'll have a special focus on the Grignard reaction and hope you enjoy watching this video. So a Grignard reaction is actually one of the most common kinds of organometallic reactions. And that's when you have something that looks like this, essentially an alkyl group bound to something that looks like a magnesium and a bromine. And guess what that reacts with? A carbonyl carbon. So let's start by taking a look at this problem. What you have here is a Grignard reagent for which this bond is fairly high in electron density. And you have a carbonyl carbon right here that's pretty low in electron density. So let's see how they react. This bond attacks, pushes these electrons up, and you get something that looks like this. Now you might notice a couple of strange things on the structure. First of all, why did the CH3 go by itself and taking these electrons and attach to this carbonyl carbon? And secondly, why is this MgBr just randomly hanging out with the oxygen up here? So in order to try and answer these questions, let's take a look at the Grignard reagent itself. So what do you have here? A carbon and a magnesium, which is a metal. Now, metals have really low electron density in comparison to a carbon. So in this bond, where do you think the electrons are going to lie? They're going to be much closer to the carbon. So now if you use this bond to attack something, the electrons, for that very same reason, are going to go along with the carbon. But what about the MgBr? Why does it go and hang out with the oxygen in the previous step that we saw? Well, that's where the analogy comes in. Think of MgBr as a really insecure person. What happened right now was that carbon just took away all of its electrons that it was previously sharing, and now it's left all alone without its electrons. Really, really insecure. So in order to sort of compromise on that, it's going to try and hang out with someone who has a lot of electrons. And who do we have? The oxygen. So with that, let's take a look at the first step of the reaction once again. So like we talked about, the CH3 group attaches directly to the carbonyl carbon, taking the electrons in the bond along with it, and the MgBr sort of hangs out with the oxygen because of its insecurity. But let's just wait for a second and imagine what the structure would look like if these two were not bound together. The MgBr is left feeling sort of empty with a positive charge without its electrons, whereas you have this oxygen here with a nice big negative charge. And so now the insecure magnesium decides to form this bond with the oxygen so that it doesn't feel too empty and alone. And the oxygen, it's O-, it's popular, it's too self-involved to even notice the magnesium, and essentially goes on to behave like this as though it still has all the electrons. So although it's technically bound to magnesium, it still behaves like this O-, and you'll see what I mean by that in the next step. So if you'll notice, we have a tetrahedral intermediate, 4 things attached, and we're in basic conditions, so this is a leaving group that can just leave directly. And so the oxygen is still behaving like an O-, right? So it can still collapse on itself using these electrons from the bond and kick out the leaving group. So the oxygen essentially ditched the MgBr, taking those electrons back and ignored it, and used it to reform this double bond right here, creating another pi electrophile here. This carbon is electrophilic. So it can be attacked by another Grignard reagent, and it acts the same way again, producing this product. And like you can see, the carbon ditched MgBr, took those electrons again, attached to this pi electrophilic carbon, and the MgBr, feeling insecure, hang out with the oxygen again. Now, in a Grignard reaction, once the carbonyl carbon is done reacting with the Grignard reagent itself, we add acid into the solution as part 2 of the reaction. Now, we talked about how the MgBr was just sort of hanging out with the oxygen, but that the oxygen was really too self-involved to notice it, right? But the H+, a hydrogen, is way hotter than an MgBr. Get it? Hydrogen, hot. So anyway, the oxygen notices the H+, and just decides to ditch MgBr, take those electrons, and attach to the hydrogen. And that gives you this product, which is pretty much the final product of the Grignard reaction. But what happens to poor old MgBr? The poor guy got dumped multiple times, but you know what? It doesn't really stick around and be positive for the rest of its life. No, it's gonna go and do something else, take matters into its own hands. So what actually happens is that water that's present in the solution attacks MgBr to form this, and finally a hydrogen is lost, deprotonate that, and you end up with this product. And that is actually a pretty sticky solid. So now the OH and the MgBr, they're stuck together. MgBr isn't ditched again. And this isn't one of those things you typically show along with your mechanism for Grignard reaction, but this just in case you're curious about what really happens to the MgBr in the end. So let's do a quick recap of everything that we talked about today. From the very first step, you'll notice that in the Grignard reagent, carbon is a lot more electronegative than magnesium, and so the electrons in the bond, when it attacks the carbonyl carbon, they go along with the carbon, ditching the magnesium bromine. And now the MgBr feels insecure without its electrons, and so it hangs out with the electronegative oxygen. But the oxygen is essentially too self-involved to even notice MgBr and goes on pretending as though it's not there. And so it collapses the tetrahedral intermediate, and even the next time when MgBr is attached to the oxygen, it goes along and grabs the H+, totally ignoring the MgBr. And finally, the H+ is a much more hotter or more attractive option than MgBr, which is why oxygen goes and grabs it. And so you can see how the Grignard reaction is really somewhat like a story, with each group having its own persona, which makes it behave in a certain way, which might sometimes look odd to you considering some other organic chem reactions, but when you think of it like a story, it seems to make sense. You'll also be able to apply the same analogy to other organometallic reactions, and then you'll start noticing the similarities between Grignard and those other reactions. I hope this analogy was helpful. Thank you for watching.